All right, so this is the section 6 of chapter 2, and you'll notice in your notes that this section is a little bit longer, so I'm definitely going to have to break up this video into parts. So this is part 1 of section 6 in chapter 2, and we're talking about rational functions and their graphs. Now let's talk about rational functions really quickly. Rational functions are functions where we have a polynomial over another polynomial. So that's what we're seeing here. We have some polynomial over another polynomial. And we want to be careful and make sure that our denominator is not equal to 0 because we can't divide by 0. So the domain of a rational function is the set of all real numbers, so all real numbers, except the x values that make the denominator 0. So we need to be careful that in our domain we do not include what would make our denominator 0. So let's look at some examples really quickly. Our first example here, we have our function here, and on the bottom, all we really care about is what's on the bottom. And we want to see what would make my denominator equal 0. Well, 0 would make the denominator 0, 2, and negative 5. So we know that x cannot equal 0, 2, or negative 5. Well, the way we want to state our domain is typically going to be in interval notation. So my domain then is going to be negative infinity all the way to negative 5. Then from negative 5 to 0. And then 0 to 2. And then 2 to infinity. So that's our domain for this function. Now we can look at the next example. And this one's not factored for us yet, so we need to factor the denominator. Thankfully, this one's pretty easy to factor. So we have x plus 3 and x minus 3. So we know that x cannot be equal to positive or negative 3. So you can state your domain like this. Or if it's a short answer question, you can say this. So all real numbers except plus or minus 3. Okay. And that's fine for a short answer question. A multiple choice question is typically going to have an answer like that. Looking at the next one, if we're trying to think what would make my denominator 0 here, you can play with different x values, but you'll see pretty quickly that there's no value that I can plug in here that's going to make my denominator 0. So if there's no values that would make my bottom or the denominator here, if there's no values that would make it 0, then we can just say all real numbers. Okay. Zooming back out here, what we're calling these values that we can't plug in, or the values that would make my denominator 0 here, those are called excluded values, and you're going to see this term over and over again. So these are values that we cannot plug in for x. Now, kind of changing gears here a little bit, we have the reciprocal function, and 1 over x is the most basic rational function. It's a basic polynomial of 1 over a basic polynomial of x. And just to kind of discover what this function actually looks like, we're going to go ahead and plug in some values on this chart here. Now if I plug in 1 over 100, I have negative 1 over 100. Plugging in negative 10, we have negative 1 over 10. Plugging in negative 2, we have negative 1 half. Plugging in negative 1, we have negative 1. Negative 0.5 is going to give me negative 2. Plugging in negative 0.1 will give me negative 10. Negative 100. Plugging in 0. We know that that can't happen, so I'm just going to leave that blank for now. Plugging in 0.1, we can see that we're going to get these same values, but just positive. So 100, 10, 2, 1, 1 half, 1 over 10, 1 over 100. Okay. If you're not sure how I got these, you could use your calculator and divide, and you'll see that's exactly what you get here. Now I left this one blank. And that's because if I plug in 0 here, well then we're dividing by 0, and we know that in math we can't do that. There will never be a point in math where all of a sudden now we can divide by 0. So we're going to say that this is, I didn't leave enough room here, but this is undefined. Okay. So this is undefined here. And that's what we'll say happens at 0, is that the function is undefined there. Now that we have some points here, though, let's go ahead and graph what our function looks like. I'm going to zoom out a little bit more here. Okay, so I've got my table here, and I'm not going to plug every single value in, but I'm going to make a big enough picture here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we've got a good enough amount of values here. So let's go ahead and graph our function. Now at 1, plugging in 1, we got 1. At 2, we got 1/2. At 10, we got 1/10, so really, really small decimal there. Maybe I should zoom in on my graph a little bit. At 1/2, we got, let's see, at 0.5 we got 2. And then at 0.1, so even closer to 0 here, we got 10. Okay. So looking at these points here, we can see that our graph is really, really steep and then really, really flat. And let's just kind of look at this piece for a second here. If I even plugged in 100, it's still going to keep getting smaller and smaller and smaller, but there's no value that I can plug in that will make it equal 0. No x value will make this function equal 0. And something similar is happening here. I'm plugging in values closer and closer and closer to 0, but they're still not equaling 0 here. They're just shooting off really, really, really big, becoming really big numbers. Now looking at the other side of our graph, if I'm plugging in, let's see, -0.1, or -0.1 right here, we have -10. And then -1/2 gives me -2. -1 gives me -1. 2 gives me -1/2. And -1/10. And so we're seeing something very similar happening here. Now it's not actually going to touch, and my graph is not perfect. I think it does touch in a few places. But we can see that our graph has this very exaggerated kind of L-shaped curves here. And what's happening at the y-axis here is we have a vertical asymptote. It's a value that my function's getting really close to, but it doesn't actually equal. Okay, so again, we also have a horizontal asymptote here. My graph is getting really, really close to the x-axis, but it's not actually touching it. Now, if we flip to the next page, so I'm going to go ahead and leave this here for a second and flip to the next page, we can describe what's happening here using this arrow notation. Okay, so we can describe as x gets closer and closer and closer to a from the right, this is the symbol that we're going to use. And you can continue to see the other symbols that we're going to be using here. Now, it's really best to describe these using a graph. So what we're going to do is now we're going to graph the next basic rational function, 1 over x squared. So rather than making a table, I'm not going to take the time to make a big table like I did last time, but I am going to just kind of verbally say what these values are. So let me go ahead and write out our graph here, set it up. Okay, so now looking at our function here, if I have 1 over x squared, well, I still can't plug in 0 because that would be undefined, and so you can probably guess we're probably going to have a vertical asymptote right there. I can plug in 1, and plugging in 1 gives me 1. Plugging in 2 gives me 1/4, so it's getting closer to the x-axis even faster. Plugging in 3 gives me 1/9, and I'm just going to continue to get these really small fractions here. Plugging in 1/2 actually gives me 4. So not only is it shrinking faster, but it's growing faster as well. And so we can see this right here is what our curve looks like. Okay. And on the other side, because we're squaring it, when I'm plugging in negative values, I'm not getting something down here. I'm not getting something negative. It becomes positive when we square it. So it's going to look exactly like the other side. So this is the graph of 1 over x squared. And now we're going to use the chart above to describe what's happening here. So looking at my graph and my chart, let's see if I can fit both of those in here. Okay. As x is getting closer to a from the right. So let's say a is 0. So as x is getting closer to 0 from the right side, so my x values are getting closer and closer to 0 from the right side, my function is getting larger and larger and larger. So the way we can describe that is as x goes to 0 from the right, f of x goes to infinity. Now what we're doing right now is a concept that is crucial for you to understand in calculus. So make sure that you really understand what we're doing here, and if you don't, feel free to ask questions during class. Now we can also approach from the left. So if I'm approaching 0 from the left side, so as x goes to 0 from the left-hand side, f of x is shooting off to infinity. It's going to keep getting really, really big here. So f of x goes to infinity. Okay. Now we can also describe as x goes to infinity. So as x goes to infinity, so my x values are getting bigger and bigger and bigger off to infinity, my function, or f of x, is getting closer and closer and closer to 0. So as x goes to infinity, f of x goes to 0. And we can also say as it goes to negative infinity. So as x goes to negative infinity, getting further and further large negative values, my function is getting closer and closer and closer and closer to 0. Okay, so that's how we're describing what's happening here. And just like before, we have a vertical asymptote here and a horizontal asymptote here. Now, like I said, this is a concept that we use in calculus a lot, the concept of a limit. And in fact, this very page I showed to my calculus class this week. So they already have seen this, and they're having to remember it from pre-calc. So we're talking about what our function f of x is doing as x is approaching certain values. And I'm going to stop part 1 right here, and then we'll pick up with vertical asymptotes of rational functions in part 2 of chapter 2, section 6.